Welcome to Chapter 14 for CHEM152. This is coming off of Exam 3, so you've just now got some homework posted for Chapters 13 and 14. That Exam 3 will take a little bit of time for me to get back to you. But now take a look. I've got what you have ahead of you, okay? The last two quizzes, Quiz 5, Quiz 6, coming up May 12th, May 19th. Wanted to remind you, Activity 1 was assigned while we were on campus. It's due May 21st. This was one where you needed to attend a seminar. Some of you attended seminars on campus. That's fine in person, and if not, look at the activity. You can watch video of it and attend the seminar virtually. This is the last week. May 8th is the withdrawal date, and if you stay in, then this is the plan. Okay, we revisit the class theme. Remember, this was how is taking chemistry like being an Olympian, what we can learn from the Olympic Games. There's been a lot of adversity this semester, but I really hope you keep in mind some goals. Maybe your goals have changed, that's okay. But the end is near, people, and what I really want to encourage you is finish strong. So maybe you need to make some new goals. What do you want to do this last month of the semester? What do you want to accomplish? So really encourage you, maybe that's come to office hours, maybe that's spend more time doing the homework, but really encourage you. I think it makes a difference if you finish strong. There are some good things coming up. This is actually one of my favorite chapters. So I'll be talking about acids and bases today, and these topics are all revisited in Chem 201 at a much greater depth. Okay, so it's a great class, Chem 201. That's one of my most favorite sections to teach, is this acid-base in Chem 201. So this is really laying some important groundwork. So this should really help with some concepts, and then we'll do some calculations at the end. You can see in the chapter 14 and 15, and 15 is actually quite short, but there's two days designated for chapter 15, so it'll be a nice chance to get caught up on some things and spend some time doing some other things like homework, things like that. So let's get started on acids and bases, and you're going to see that you're quite familiar with acids and bases. You can see here, maybe you've seen it in a movie where the acid is used to break out of prison, but these things are very practical. They're in our foods, they're in the products that you're around. So we'll talk about some common things about acids and bases. So I encourage you to think about, what does it mean for something to be an acid? And maybe you've heard that term, you've seen it in the lab. What are some things that make it or signify that it's an acid? Well, sour. Some of you like to cook, bake. I saw that in your registration, filling out that sheet at the beginning of the semester. So sour is associated with acids. Which is kind of funny if you think about, well, someone's had to taste these things for them to know that they're sour. Well, it also dissolves metal. That's pretty intense. Turns blue litmus paper red. We like to watch cooking shows in my family, and you'll see we need a little more acid, needs a little acidify that. That's this sour taste that the chefs are talking about. Some of the common ones are hydrochloric acid, that's stomach acid. Sulfuric acid, acetic acid, that's vinegar, balsamic vinegar, so that you can see that has a wonderful taste. That's where that comes from. Carbonic acid and hydrofluoric acid. So we talked about this in naming, but right away we should be thinking about acids as an H. Okay, usually it's written at the first of the formula. And in particular, we're going to see that H is an H that can come off as H+. So this is what signifies, and we'll talk about definitions, acids. So you can see the structure. So coming off of chapter, looking at Lewis structures and experiment 9, writing out Lewis structures, you can see you go from a formula to then a structure, and this hydrogen is one that can come off as an H+. Okay, so that's the acid part of that. Well, that's not too bad for nitric acid because there's no H's anywhere else, so that makes sense. That's an H+. And the reason, if we go back to the structure piece, is that because that's a polar bond and oxygen's partial negative, hydrogen's partial positive. So now acetic acid, on the other hand, look at all of these H's. Okay, well, you have to think about the bond that's connecting those H's. This is C to H, C to H, C to H. That has an electronegativity difference of 0.4. So those are actually non-polar bonds. So that's not going to be the acid. The acid is going to come over here. That's going to be an H+ that can come off. Okay, so it's really critical thinking about the bonds again. Okay, so those are the H+ that we're going to be looking for in these substances. The bases, similar properties that make it distinct. The taste, well, in this case, it's bitter. It feels slippery. If you ever have cleaned your oven, that oven cleaner is sodium hydroxide. That's a base, very slippery feel. When I do that, it gets on my hands. It drives me crazy. That's a base. And it turns red litmus paper blue. So you've seen litmus paper if you've had lab on campus. This is telling us, is it acidic, is it basic? So I mentioned the sodium hydroxide and oven cleaner, potassium hydroxide, sodium bicarbonate, and ammonia. So this is another cleaner, baking soda, baking powder. So those are some of the bicarbonates and carbonates. So there's some definitions that we'll want to work on. Okay, acids and bases can be defined a variety of ways. So we'll talk about a couple here that we can use, and it does depend on what kind of compounds you're looking at. So in some instances, you may call this an Arrhenius acid or a Bronsted-Lowry acid. So we'll distinguish what these terms are. So that's the two that we're going to cover, the Arrhenius and Bronsted-Lowry of these definitions, and see how they're similar and how they're different. So the Arrhenius definition really focuses on those H+ we were talking about, and the definition of an acid is that it produces H+. Okay, so acids produce H+, so had that example earlier of HCl. You put HCl in water, and it produces H+. Because these separate out into the ions, H+, Cl-. Bases, on the other hand, produce the hydroxide, or OH-. So sodium hydroxide, our oven cleaner that we talked about, separates. That goes to Na+, and the hydroxide, that's the base piece. So the problem here is that this is only in aqueous, okay, water-based solutions. So that's being very specific, and that's mostly what the chemistry we've been doing is water-based solutions, but not always. So definitions can change. So we'll talk about another definition, but I wanted to emphasize the Arrhenius acid. So I already showed the H+ coming from HCl, so that's here. And since this is in water, remember H+ aqueous signifying water, please note that H+ plus water, that equals H3O+. This is called the hydronium ion. So you may see H3O+ or H+. Those can be used interchangeably. And base here, sodium hydroxide, separated into the ions. And we talked about litmus changing color. Well, there's an indicator in here. You can see it's blue for basic, it's pink for acid. Hydrochloric acid by itself is colorless. Sodium hydroxide by itself is colorless. So it's got an indicator there to let us know, is it acidic, is it basic? So that's an Arrhenius base. So the other definition, Bronsted-Lowry definition. Now we're seeing that this refers to still the H+, but it's talking about, is the H+, is the substance a donor? So an acid is a proton donor, and a base is a proton acceptor. Okay, so now we're looking at this a little more broadly, and we're looking at what's happening, okay? Where is the H plus going? How is it being transferred? So this definitely can be outside of an aqueous. This is more widely applicable. It doesn't have to be aqueous. So when we're looking at the Bronsted-Lowry, again, we're looking at the big equation, so not just what does it produce. So this is the entire reaction. Okay, so what's giving up the H, what's accepting the H, where are the H's going, that's or our H pluses or our hydroniums you can talk about. So this is looking at the big picture. Please note, if one thing is donating or giving up an H plus, something else is accepting. So acids and bases happen together. Okay, if one thing's transferring, something else has got to receive it. So let's look at a few examples. Hydrochloric acid we showed earlier. Now you see how I'm showing it with water, and can see that water gets turned into H3O plus, and that's because it takes an H plus from HCl. So HCl gives away an H plus and becomes Cl minus. So now we're looking at the big picture. HCl gives it up. That makes it an acid. Wait a minute. Take a look here. That means water is receiving it. That means it's a base. Okay, so HCl, acid, H2O, base. One's giving the H plus, one's accepting the H plus, and that's what happens in this reaction. Another example, we can see here, this is NH3. Wait a minute, there's lots of H's here. Okay, don't be fooled by this. This is also, if you recall, a lone pair present here. Okay, so we have now water, ammonia, and you see how the ammonia accepted an H plus from water. So water lost an H plus, went to OH minus. NH3 gained an H plus, went to NH4 plus. So I really want to stress here about charges. Okay, so NH3, if it accepts a proton, that's an H plus. We have to write the formula and the charge. Okay, so this chapter is critical for formula and charge. So that's NH3 plus an H plus, that goes to NH4 plus. Okay, that's what happened here. And we can take a look. If H2O gave away an H plus, so we lose an H, and if that's a positive, that means it's got to be left with a negative. Okay, if you think about this, look on the right side of this arrow. OH negative, so that's a negative, plus a positive over here should equal a neutral. Okay, so H2O, we lost one of those, so there's only one H here, and there's a negative charge, and it lost it in the form of an H plus. So this is what we're looking for in tracing. So then we can see with the ammonia, it's a base because it's accepting a proton. And then water gives up the proton. That's the acid. Wait a minute. We said water is an acid. Here we said water is a base. What's going on? Which is it? This is the term amphoteric. Amphoteric means it's something that can be both an acid or a base. So we're going to see substances that can do that. It can accept a proton. It can gain a proton. The reason, it has an H in its formula, and it has lone pairs to accept an H. So it can do both. That's why it's called amphoteric. So another example, HSO4 minus. So I'll write this here in the middle, showing this is bisulfate. Well, I can go this direction and accept an H, that goes to the neutral H2SO4. Or if we lost an H, so that's plus an H. If we lost an H, look at the charge now. Double check here. So this is HSO4 minus. We lose an H, that becomes SO4, and don't forget 2 minus. Okay, so this is gaining or losing protons or H pluses. So when we're looking at these things, we want to match them. So we saw ammonia accepted a proton here and became ammonium. Okay, so this is called a pair. Specifically, it's called a conjugate acid-base pair. This one's a base, and this one's the acid. Okay, so if it gained a proton to go to ammonium, guess what? Ammonium can lose a proton to become ammonia. And we already saw this with water as well. If water's here, you take away a proton, it's related, it's a conjugate pair with this OH minus. So we call this the acid form, the conjugate base form. The base form, the conjugate acid form. So the idea is to look at pictures and think about, well, we've got a chemical equation. How is this related to something on the right side? And you can see, oh yeah, there's a C, there's 3 O's. Conjugates are only different by 1 H plus. Okay, so if we're different by 1 H plus, then it either gains or loses an H. So here, gains an H, becomes the acid. Water loses an H, becomes the hydroxide. All right, so now you go ahead and identify what's on the left. Is it an acid? Is it a base? And then what is its conjugate on the right? If it's an acid, what's its conjugate base? If it's a base, what's its conjugate acid? Go for it. So I want to point out, remember that water can be amphoteric. So that can be a confusing one. Well, take a look here. Well, this is related to water. We said this was the hydronium ion. How is it related? Okay, did it lose an H? Did it gain an H plus? And in this case, it gained an H plus. Okay, so that means over here, this had to donate an H plus. So that's our acid. This is our base. And then now we saw that these two are related. So if that's the base, this is the conjugate acid. So then of course, that means these two are related. If that's the acid, that's the conjugate base. So that's the one here you can see labeled acid, conjugate base, red, base, conjugate acid, in blue. Okay, so if you look at the next one, we can see here this is the bicarbonate, and if it goes to the H2CO3 form, it had to gain an H plus. That makes it a base because it takes on an H plus, and that makes this an acid because it donated that H plus. So red flag, hydroxide always should be associated with a base, so this is conjugate base. And if that's the base, that's our conjugate acid. So this is key, identifying acids, bases, and then we're going to think about their reactions. What happens when we put these two together and they neutralize each other? So this is a neutralization reaction. An acid reacts with the base, and when that's the case, the products are a water and a salt. So this is really nice. You can identify is the reactant acid, reactant base, then right away you know the products. Okay. This will be in an experiment for CHEM152L. You do a neutralization reaction and you do it to figure out some unknown concentration. Okay, so you can imagine if you had something happen, there was, the pool was too acidic or the pool was too basic, you have to test it, you have to figure out the unknown concentration. Okay, so that's what you can do with a neutralization reaction. And this is called a titration. So to titrate, what you do is you have a known, and this bracket is from last chapter, molarity. You have a known molarity or a known concentration, and you react it with an unknown, and then you're solving for that molarity. So that molarity of acid was really, really high. It could lead to bleaching the clothes or something like that, if you're talking about pool water. So this is a titration. What does this look like? Well, you have a burette, and you can fill that with your acid or your base. And then you have an Erlenmeyer flask with your starting amount. Usually this one is your known, and this is your unknown, but it can actually vary. And you start adding the titrant, or adding the burette. So you can see that the base is in the burette. So you're adding that, and the acid or the H pluses are here. And when it gets neutralized, you have an indicator in there, so when it is neutralized, it turns color. So you see this is colorless, and this is pink, and now you know you have neutralized that for this titration. So again, the burette is the top one, and our indicator is critical because these acids and bases are colorless. If you forget to add indicator, and it happens, you forget to add indicator, you're going to keep adding what's in the burette, and you're never going to see anything. Okay, so you definitely need to add indicator. And the key for the quantitative piece now is when you get to that color change, that endpoint is signifying that the moles of acid are equal to the moles of base. This is called the equivalence point. When the moles of acid equal the moles of base, so the amounts are equal, then you've got a color change. So how do we do this? Well, again, the goal is, CSI work. What's the unknown? What can we do to solve for this unknown? So you have a volume that you added from the burette, and you have the concentration that you had from the burette. Well, if you have molarity, remember right away when you see molarity, rewrite it moles per liter. So you have molarity, and you have the volume in liters. What you have is the moles of what's in the burette. Okay? Then you need to use a balanced chemical equation. Is it a 1-to-1 ratio? Is it a 2-to-1? So you look at a balanced chemical equation and convert. So this is our mole ratio. Convert moles of what was in the burette to moles of what was in the Erlenmeyer flask. So now you have the moles of your unknown. Okay, you've converted to that, and you started out with some volume in the Erlenmeyer flask. That volume, then you put it back into the formula, moles divided by that volume in liters. So now you know the concentration of the unknown. All right, so let's go for it. Here's the titration of 10 mils of hydrochloric acid, and that's your unknown. And your known is the burette had 12.54 mils titrated, and it was titrated with this 0.100 molar sodium hydroxide. The color changed. That was equivalent. Moles equal moles. Okay, so what's the concentration of HCl? Let's go ahead and pause this, go for it, solve for concentration of HCl. What's important to think about is the chemical reaction. This is hydrochloric acid. This is sodium hydroxide. That's a neutralization reaction. Right away we should be thinking if it's neutralizing it, that's going to a water and some ionic compound. So water and a salt. And in this case the salt is made up of this cation, Na, and this anion, Cl. So that's our reaction. So we need this 1-to-1 stoichiometry here. And then now we need to look at our burette. That was the sodium hydroxide, so we took the volume of sodium hydroxide, converted it to liters, and remember molarity times liters equal moles, so that's moles of sodium hydroxide. We need the moles of HCl, so that's a 1-to-1 ratio right here. And now we've got our amount of unknown. Well, we started out with 10 mils of that though, so now we divide by 10 mils, And now we solve for our unknown concentration of HCl. So this is solution stoichiometry. It's just now solution stoichiometry of acids and bases neutralization. So let's talk about a couple of other acid-base reactions. So the neutralization, acid-base, those are the two reactants, and salt and water are the products. Take a look here. This is that acid and metal that we saw at the beginning of the chapter. It dissolves the metal, so that's aqueous metal salt, and it forms hydrogen gas. This, you can ignite it, and that's the reaction. Acid metal, a classic reaction that gives you hydrogen gas. The other, you can see example, this is another acid, another metal, same idea, hydrogen gas. And then you can see an acid plus a metal oxide. Okay, so that's got the oxygen here. That forms water and a salt. So the H's are combining with oxygen, so this is a double replacement. H goes with the O's, K's go with the CL's, so that's a double replacement of the acid and metal oxide. So most of this was conceptual. We did a little bit of stoichiometry there, but now we're going to get into a little bit more concepts that lead to some calculations. Okay, so first is the acid-base strength. This can be very difficult to understand, and the problem is because it looks the same. So hydrochloric acid is a strong acid. However, hydrofluoric acid is a weak acid. Those look the same. There's an H out front. There's a halogen next to it. It's confusing. It's strange how one's strong, one's weak. Well, these things can have different strengths. What does this mean? Well, the more weak acids and bases are available, so there's only a few strong acids. So the nice way to do this, I'll talk a little bit about what we do in our class, but in my Chem 201L class, there are 6 strong acids, 6 strong bases, commit to memory, and then if you see any other acid and base, you just assume it's a weak one. So that's one way to do this. Acid-base strength goes back to solutions in terms of electrolytes. Is it a strong electrolyte or a weak electrolyte? So the question is, does it ionize completely? Okay, so what that looks like is, over here, HCl is a strong acid, and it's a strong electrolyte. So if you take a look, all of these are ions. All of these have charges. Okay, so strong acid, strong electrolyte. There is no neutral HCl molecules together in solution. That's all free ions. Sodium hydroxide is a strong base, so we're talking about strong acid, strong base. They are all strong electrolytes. So then you can see again, all free ions here. There's no neutral NaOH. What a weak would look like, showed you HF earlier, is if you put HF in water, you would actually have a lot of HFs. So maybe I'll make a beaker here. So all of these HFs, all of these HFs, and it would be even more than what I'm drawing here. And then be a very small amount of charge. Okay, so actually, it'd be like 5% of it is actually charged, H plus, F minus. 95% is neutral, HF, HF. So that's a weak electrolyte. So this is strong, sodium hydroxide, HCl. This is weak. So we'll get to this here shortly, but I wanted you to see together the importance of all of these ions. And there's only very few ions when we get to the weaks. So this is a list. What I want you to be familiar with is a couple of strong acids, a couple of strong bases. What that means is can identify 2 strong acids, 2 strong bases. So hydrochloric acid you use have used regularly in lab. Look, hydrobromic acid, very similar. Hydroiodic acid. Some of the other ones with the oxygens, nitric, perchloric, sulfuric, and the hydroxides are the strong bases. So you just know these three, the alkali metals, lithium, sodium, potassium, you got some strong bases memorized. Here you can see this is the alkaline earth. They also are strong bases. So now the weak that I mentioned, it showed you the HF earlier. You see how this very small amount of charges. Same thing, ammonia is a weak base, very small amount of charges. So they do not disassociate. They stay as these molecules. They do not form ions. So how do we distinguish between these? I just said HCl, HF, they look the same. Well, here's how we do it. The arrow here, okay? When I've done this with HCl, I show a single arrow, which means that goes to 100%. Okay, this fully goes. And I said earlier, this doesn't. This is like 95% HF, 5% ions that form. Okay, so that's why we have this double arrow. This goes to the right, forms products, but also the products go to the left and form reactants. So that's a double arrow. Equilibrium, we will cover equilibrium next chapter. But this is the difference. So this is a weak acid double arrow. So now we're getting into some calculations, okay? We've got to have these concepts down in order to get there. Well, water reacts with itself. What does that mean? Okay, so H2O plus H2O, look at this, double arrow, H3O plus, OH minus. Okay, so it's reacting with itself. We said water can be an acid or a base, and this gives us a reaction. Water plus water equals this hydronium, remember we've said represents acid, and hydroxide, which represents base. So this double arrow tells us there's an equation that relates what's on the left to what's on the right. And this equation gets us to the water ion product, and this is the key, it's a constant. Okay, so the H3O plus was the product, the OH minus was the product. Well, those form in 1-to-1 stoichiometry. That means they're in equal amounts. Okay, so the product, the H3O plus, it's 1 times 10 to the minus 7. The OH minus is 1 times 10 to the minus 7. So if you multiply those together, you get this Kw. That comes from that equation, water reacting with water, and it's the equilibrium constant, and that comes from that double arrow. We have a double arrow, we have a K. So this K equals the products, H3O plus times OH minus. We said that's 1 times 10 to the minus 7. 1 times 10 to the minus 7. So you multiply those two together, this is your constant. At 25 degrees, it's temperature dependent, but the K equals 1 times 10 to the minus 14. So what I want you to see here is that if we have H3O plus 1 times 10 to the minus 7, OH 1 times 10 to the minus 7, then those cancel each other out. It's not acidic, it's not basic, that's neutral. Okay, so that's the point we're talking about right now. So we don't always have neutral solutions. We can have acidic solutions, we can have basic solutions. So how do we get there? How does that happen? Well, if you have an acidic solution, that means you have more H3O plus. So if you have more H3O plus, okay, so remember this is a K equals our H3O plus times, and this is concentration, remember this is in brackets, it's concentration, times the OH minus equals a constant. So if we have more H3O plus, so the H3O plus goes up, and this is a constant, the OH has got to go down. Well, what if you have more OH minus? That's a basic solution, because that means you have less H plus. Okay, so the 1 times 10 to the minus 7 is the break-even point. If it's more than that, then the other one has to be less than that. Okay, that's our reference point, if you will. So, the K by definition is a constant. So as I just mentioned, the other adjusts based on the one that you know. Okay, so let's take a look what this means. Conceptually, I would be thinking, if I have this equation, calculate the OH minus, okay, and determine whether the solution is acidic, basic, or neutral. My reference point is 1 times 10 to the minus 7. So what I first want you to do is just think about, is it bigger than or less than this? Because this is a strange number, right? Small number, 10 to the minus 7. So this 7.5 times 10 to the minus 5 is a bigger number than 10 to the minus 7, okay? So if the H3O plus is bigger than that, that makes this acidic. Here we can see that it's less than that. That makes it basic. And here, oh, that's the golden point. That's the neutral point. C is neutral. You'll be given the constant, but remember that the K is 1 times 10 to the minus 14, and that equals the H3O plus times the OH minus. So that's how you can set up these equations and actually solve. So that's the K divided by H3O plus, and you get the OH minus. So remember, we can look at the H3O plus and say that's bigger than 10 to the minus 7, so it's acidic. Or you can say that the base, the OH minus, is so much less than 10 to the minus 7, it's acidic. Either way. This one you can see now the OH is bigger than 10 to the minus 7, so that makes it basic. And we saw the neutral point where they're both equal to 10 to the minus 7. So this is confusing, right? 1.3 times 10 to the minus 10, 6.7 times 10 to the minus 6. This can be hard to use. There's got to be an easier way. So maybe you've seen this talking about acids and bases, and that's the pH scale. Okay, so this is a little bit easier to work with. Okay, your neutral point is pH equals 7. And if you go higher than 7, that's on the basic side. So that's weak, that's strongly. If you go lower, that's on the weakly acidic, strongly acidic side. So this is the scale. This can help us change those numbers into something a little bit more manageable. So for me, it's a little easier to see 7, 6 is less than 7. Okay, that's an acid, versus 10 to the minus 6 versus 10 to the minus 7. That's a little more difficult, I think. So let's talk about how we're going to use the pH scale. So this is a log scale, so this is a mathematical function. Maybe you've had this, maybe you haven't, but you want to locate the log button on your calculator. And pH equals the negative log of H3O plus. So actually what I want you to see is that P just means negative log. Okay, so if I do POH actually, guess what? You can see it's still going to be negative log, and it just needs to be of what you named it. So that's the negative log of the OH minus. So that's how you calculate pH. This is a log scale, so 1 unit, so pH of 1, pH of 2, that's a 10 times difference. Okay, so it's a significant difference. Got some bad news. Okay, it's a different type of math. Well, if it's a different type of math, there's actually a different type of sig fig rule. Okay, so I think it can be applied pretty quickly, but I just want to emphasize that there is a difference. The difference, okay, so this is the pH side. pH equals 3.00, pH equals 4.52. So what I'm pointing out here is that this is just a placeholder, okay? That's just giving you a reference of the scale. So you don't look at that for sig figs. You look at the decimal places. So if it's 3.00, that's 2 decimal places. That means the actual concentration, this is the molarity, had 2 decimal places. If your molarity had 3 decimal places, or 3 sig figs, 1.003 sig figs, then it should have 3 decimal places. So let's do some practice with that. Again, make sure you locate your calculator with the log buttons and take a look here. Calculate the pH, that's what we've just been working on. pH equals negative log of H plus. You're given the H3O plus, so take the negative log of that. And then also determine, is it acidic or basic? You're given the OH this time, not the H plus, and calculate the pH. Go for it. So again, make sure, locate your calculator, plug it in, and make sure when you do negative log 1.8 times 10 to the minus 4, that you end up with the answer 3.74. Depends on your calculator what order you have to go in. My calculator, I'd put the negative, the log, and the number. Some calculators, you'd actually put the number, the negative, then the log. So it just depends what you've got. So practice with that. Over here, it's a little bit different though. You have the OH minus, not the H plus. So the first step is to get the H plus. Okay, how do you get the H plus? You get that from, remember the KW, 1 times 10 to the minus 14, divided by the OH. That gets you your H plus. Okay, so now we have the H plus. And then we can go back up here and say pH, that's negative log of that number, H plus, negative log 7.7 times 10 to the minus 13. That gets a pH of 12.11. That's above 7. That's basic. Remember, this was below 7. That's why we went to the acidic piece. So those are the calculations to finish up acids and base. We've just got one last concept, these next 2 slides. And maybe you've heard this before, something that resists change, okay? In biology, this is a really important concept, and that's what's called a buffer, okay? So if you have free acid, free base around, something's got to capture it or react with it and resist changes in pH. So a buffer, by definition, resists changes in pH. So this is a buffer. Maybe you've heard this term before. People talk about, oh, they're a buffer, their business or their family or whatever. But this is, resisting change. Okay, so it's keeping things at a certain level. Maybe it's a buffer of pH 7. That just means that it's a neutral buffer. Or guess what? You can have buffers at 4, 7, 10. You can have buffers at any pH. What it means is if you added some acid, you added some base, it's still going to be around the starting point. It's still going to be around 4 if it's a pH 4 buffer. How that works is, if you take a look, it's made up of this C2H3O2 minus. That's acetic acid. I don't know if you recall, but that's a weak acid. So if you have a weak acid and its conjugate base, you have a buffer. Okay, so what that means is, here's the weak acid with the H. Here's the conjugate base without the H. So then if an acid gets thrown in there, it reacts with the conjugate base. If a base gets thrown in there, it reacts with the weak acid. That's how these things neutralize added acid, added base. Come see me during office hours if you'd like to go over acids and bases.